Okay? So I'm going to get quickly beta operated onto u and alpha operated onto v. But u is UAEA. So this would be UA
beta B
beta of EA times alpha of VB and alpha of EB. Okay? Alpha of EB. Now give these guys a name. So we'll give this product name. I can keep it as it is if you wish. But let me give it a name. And the name that I am giving is this TAB subscript. Okay? TAB. Order is important. So what would be the interpretation for TAB? That you are taking the beta, the first, okay, and operating onto the EA, and then EB, and then multiplying, and then product is this guy. And what did you get on the other side? UA and VB. So keeping in view this interpretation, tell me something sensible about this guy. Keeping in view this interpretation, what would be something sensible that we can say about this expression after?
TAB times.
Yes. Yes. So you see, you got it. So what did you have is that you have a beta tensor product alpha operated onto UV is a TAB, okay, multiplied by epsilon A tensor product epsilon B operated onto UV. And this is true for all UV. So I can even remove this UV. So what did you get? So you have an abstract bilinear form, okay, and you can write it as a linear combination of these tensor product which we are claiming to be the basis actually, okay, and these are the components. Okay, so it all makes sense. Are you getting the point? And think about it. So in other words, what essentially you can observe that all bilinear form, in other words, 1-1 tensors, okay, can be seen as the tensor products, okay, and the tensor products are also, 1-1 tensors actually. So there is, what do you call this kind of a relationship? So whenever I was saying that, okay, when I have a tensor of which is a map from U to V, okay, and it's acting on UV and giving me some Tij and some images here, okay, I can see this abstract 1-1 tensor also as a bilinear format. So these are not two different things. So you can treat the thing as a kind of same thing actually. Okay. Is it making sense? So are we happy with this conclusion? Alright? I know it's getting messier, but once you make sense of all this, with a relaxed mind and make yourself comfortable with it, you will see that what these guys are doing is peanuts. It's nothing. Okay? And everything will make sense to you. Okay? The trouble with the book and these notes is that they are not explaining the notation. So they're calling a tensor, so like this point, so it's like a metric, the inner product is, this tensor, so covariant, contravariant tensor, like why it is, I'm not explaining it. So it's good to have a look at this abstract thing. Is it making sense? So are we happy with the tensor space V star V star? Now tell me, what would be, tensor product of V star with V star? So it would be, alpha, beta, gamma, their tensor products are equal to, A, B, C, and epsilon A, tensor product epsilon B, tensor product epsilon C. You really generalize it. Instead of having, so in other words, this would be the collection of all trilinear maps actually. Bilinear, but the trilinear map, which is linear and all components. But you are creating them, so from where those trilinear things are coming in, so they are coming from alpha star, V star actually. Okay, so I'm not using any outside machinery to define it. Okay. Now this case called, I can give it a name. So what name should I give? So it's a tensor product space. So you should call it a tensor product space because it contains tensor product. Okay. But what rank we should assign to it? That's a tensor product space of what? So it's 0 to 2. Okay. So it's a collection of 0 to tensors. And how about this one? It's like a 0 to 2.
Sir, 3 0.
3 0. So should be 3 from, because we are not taking anything from the world. Is it making sense? And I can increase as much as time I want. Okay? So the general notion that I can write is that, okay, you are taking the tensor product from I equal to 1 to n of these, bi stars. For the finite, we can make sense of what these are. It contains n linear forms. Anyway, can I see V star itself as a tensor product space? Yes, actually, it's a kind of a degenerate kind of a case actually. It's also a tensor product space. Okay? Why? Because it contains like a tensors of rank. Okay? Here's an interesting thing. How about instead of taking, say, product from V cross V into R, let's do something else actually. What should be something else?
From dual to R.
The dual to R actually. How about this one?
Dual
V star plus V star.
Dual there.
And as a result of this, okay, let's consider that such kind of maps, okay, which swallows what do you call two co-vectors and gives you a real number. Okay.
Sir, it's from which? हमने ये tensor products से लिया.
No. So it must be simple cross product.
Simple.
Yes, simple cross product. Not the tensor product. Here's it. अच्छा, इसके corresponding जो space होनी चाहिए. What name should it give? Okay, I can explain it. Okay, what does it going to look like? It's going to be simply the repetition of everything that you have done here. What thing should, so it's like, what should be the collection of all such linear maps actually, bilinear maps. So naturally we should give it a name, V star, tensor product class V star. But since we are in finite dimension, here's a very interesting thing. Since we are in finite dimension, you can prove that V star is actually V itself. So it's really isomorphic, not equal to, but
Isomorphic.
really isomorphic. getting the point? Okay. So it's V. So in other words, the tensor product of space that you get out of this is nothing, it's just V tensor product V actually. Okay. Why this would be the case? In other words, how can I see a vector in R3 to be a map from V3 into in other words, take an alpha, which is a covector, and take a V into it. Okay, it's like operate V into the map. So it's like it's a pretty strange thing. So far you have understood that. Okay, you can you can take a point and put in a function, but now you have other way around. Okay. So the question is, how can I create a number using these two? It shouldn't be a difficult thing. So what I just need to do, I need to just create a number out of it. So it must be. You can see that it's a linear map. If I can see even the vectors as a linear map, so it's like V of alpha plus beta would be alpha plus beta operated onto V and so on and so forth. Okay? I get the point? And this is not something strange actually. It's not something strange. Think about it. Haven't you done this? Can't I see, think about it, you have seen something like this already, because when you are talking about, for example, the coordinate transformation, how does the coordinate transformations are working actually? So what is the definition for the coordinate transformation? For example, a simple one, standard one, the basic one from where we started the lecture. Like, okay, this guy seems pretty alien to you, but it's not that alien actually. It's a simple object. Okay. So what key thing you have to keep in head is that here these maps are changing all the time while the V is fixed. So if we are taking the maps, okay, from V star and then operating it onto this one fixed vector, and you're getting the numbers as an outcome. So in this sense you can get. Anyway, are you getting the point? So what? So this would be, so if I have such kind of a linear map, I'm going to define it in a moment. How does it going to look like?
0 to 10.
It would be, so this space is nothing, just tensor product of V with itself. Because V star star is V and V star star is V as well.
मतलब 0 to tensor, so 2 0 tensor वो isomorphic होगी क्योंकि V star plus V star में तो 0 to tensors हो गए.
So V star is not necessarily isomorphic to V. It can't be. Think about it. So we have just seen that this is the 16-dimensional space actually. If you take V to be 4-dimensional, okay, so it's not necessary. So in other words, if again. So it's not isomorphism is not isomorphism with the dual is not necessary, but the double dual is yes. With the double dual, yes. Okay? Alright. So let's explicitly write. Not to spend too much of time, I'll just directly write the result. So what essentially I want by doing all this is that you should learn this language actually in which the things are written. Otherwise you'll be stuck at every point. What is going on? You'll have no clue and no idea. So once you learn this language, it's not that difficult, it's just simple linear algebra. in my opinion, this should be part of the advanced linear algebra course actually. Okay, so what is V tensor product V? If V is the vector space, so it's a collection of maps of in other words, the tensor product of the vectors from the V. So it's like a U tensor product V. Okay, so that U tensor product V is a map from V star to V star into R, okay, and is bilinear. And it's bilinear, so it's like a linear in both components as well. You getting the point? How does it going to work? So it's like if I have a U tensor product V and operate it on some alpha beta. Okay.
U of alpha and
Alpha of U.
You must get what?
alpha beta.
U of alpha and
V of beta, which is same
The same as alpha of U.
alpha of U or beta of B.
It's the same as alpha of U, beta of U. And what you can ultimately write is that I can write this as Tij, you know, with upper index, multiplied by the tensor products of what? Tensor product of what? Of the basis vectors of V. So in other words, EI tensor product Ej. So this is how, you know, operated onto alpha beta. This is how, you know, these tensor products are going to look like. Okay? Are you getting the point?
सर पर ये दोनों सेम नहीं है?
What do you mean by that?
Different is subscript is.
By definition. सर अगर सिर्फ हम तो definition लगाएं, and then it will be alpha of U times beta of V, and then this is the same thing here.
Alpha U and but like okay.
This may be the
U
alpha star
and
beta.
V are arbitrary actually. So it's like okay, then maybe okay, I must use some different symbols actually. Okay, so here beta and alpha are fixed while U and V are arbitrary.
So but okay, so when they are fixed, when they are same,
They agree. Yes.
so they agree each other.
Yes. Yes. Okay. Is it making sense? This is how it is. They are of same nature actually. Yes, actually that's what we can say. Is it making sense? So these are what you call bilinear forms. Okay. So when we first defined just RS tensors, we defined them as an abstract object. But what we are doing now is that we can create such an object actually by just taking V and V star. That's it. Okay. So you take the V and its dual, and then you can create all such objects. Okay. Now let me. Okay. So what would be a, you know, a generalized tensor product space actually? Okay. Generalized tensor product space. How does it going to look like? How does it going to look like? That you take the R copies, okay, of V. But before doing that, shall we not, okay, do for example the tensor product of V with V star actually first and then generalize it actually, rather than I'm going too fast. So what would be this? So this would be the collection.
V tensor product with alpha.
Okay, so this is interesting. Now the two, so it's like two different species are talking to each other. You know, so it's like one is vector, another is covector, but still you are kind of, you know, making them talk. Okay. So it's like U tensor product alpha, okay? But the U tensor product alpha is a map.
One cross one.
V dual cross
So,
V
so it's going to be opposite.
opposite.
So it's like a V dual
Cross V to R.
V into R. Ah, okay.
So why opposite?
और V क्लास वन क्लास V
U के ऑपरेट चाहते हैं अल्फा या बीटा दे ऑपरेट करने से
Okay.
कर दो
Is it making sense? So it's collection of all such things. Okay. And give me a guess. How can I write U tensor product alpha? I don't want to write in this manner. So just tell me that how does it going to look like? So this would be D,
I J
and where would be I and where would be J?
I sir above sir
I above and J below. Okay. Of EI tensor product. Not so strange. Learning gradually this language.
operating on U command.
Forget about it. This is not that how does this is how these abstract objects look like.
ओवरले दिना है
ठीक है जी. And then I can generalize all these things. I can take them to the new level where you have V copies of R copies of V, and S copies of V star. Okay. So like maybe these are R copies and these are S copies. So how does an inhabitant of this space is going to look like?
Sir, EI tensor product epsilon J उसको कैसे define करेंगे?
I don't know. Think for yourself. So you have to find this and this. Maybe you need some combination of both. So it's not that
V
difficult.
star class V
You can have a guess.
We haven't defined it.
I don't want to define. I wanted that you should figure out for yourself actually then. Actually with this definition. Alright? So how does the inhabitant of this is going to look like? So this could be a map from the R copies of the dual. It's like cross product of R copies of the dual and S copies from here and then into the R. Okay. Usually the convention is this. Let me make a little bit of correction. Usually you take, if you see, this is in a bit contradiction with the things that we defined previously. Because if you see, we in the beginning we defined multilinear maps from some copies of V to the copies of from the some copies of dual into R actually. Okay. While here you have this opposite order, and this order is important actually. Okay. So if you have so it's like so it's like I must put in a star here, so that I can put a V here and V star here. So it's going to make more sense now. So let's change accordingly. Okay.
to
So
alpha
get a
alpha U
alpha here, and maybe a U here, and then epsilon I here, and EJ here, and so on and so forth. Okay. You can ask several kinds of interesting questions. Can I have this kind of in space? Okay, so something like that. Maybe something like that, something like that. Here was on something like that. The answer is that in principle, mathematically, you can have such tensor product space. No one can stop you from doing it. But you don't call such quantities as tensors actually. So for tensors, the convention is fixed. And the convention is what? That you have to first take the copies of the vector space, and then a cross product of the copies of the vector space, and then the copies of the cross product of the dual spaces actually. Okay? So if we stick to that definition, then only such kind of things make sense actually. Not this kind of thing that I wrote earlier, or maybe this kind of. You can define it. So in defining it, there isn't a trouble. But but we will not call them tensors. Okay. So tensors are the maps, some copies of vector spaces and some copies of a dual into R. The last thing, if I try to define it, what would be this space in general? Okay, so I have written it here. So I need to put a stars here.
First. And remove star.
Star from here. So it is going to be the
collection
of all such maps which has R copies of V's, which takes kind of R inputs as vectors and
S inputs as maps.
Okay. And how does it going to look like? So if I generalize, so it's going to look like how? So it's going to look like this actually. So I'm directly writing. So it looks like, okay, I1, I2, what do you call R, and J1, J2, and Js multiplied by
epsilon
these, okay, the product of these duals actually. Okay, so it's like, okay, EI1 or epsilon? Epsilon I1 tensor product epsilon I2 tensor product epsilon IR tensor product E J1 tensor product E J2 tensor product E J S actually. Okay. So the thing that I was doing in the beginning, okay, that what physicists are usually doing. So see, if you have, I mean, if computationally, if I wish, I can get rid of these quantities. What do I mean by that? Let me give you a precise hint. So in other words, if you want to do computation in R2 or maybe R3, such kind of statements are enough actually. So it's like, okay, you have 2, 1, 3, and you want to take their dot product and cross product, and then you want to compute angles and this and that. You can do, so if you have a force, of this nature, and displacement is this, and take their dot. So you can do all kind of things by using such a notation where the components, if the components are there, everything is fine. You do not emphasize on writing in this way that, okay, you have this 1i plus 2j plus 3k. Because using this notation, these ijk's are redundant actually. It's just an extra thing. But they are there. They are there. So what physicists are usually doing, the young people actually, I'm not talking about, senior guys. Okay, maybe they knew everything. So they are just kept in for them this is vector. Well, we know that these are not vectors, these are just components. You just listed the components of vectors actually. So even for practical computations, it's enough to deal with such kind of things. Okay, but the trouble is that we have to keep in our head that you have, so like this guy is this actually essentially. Okay. You can, like when I'll do computation, I'll do the way physicists do. But I'll try to keep this thing in head as well. So this is the same analogy to this actually. So in other words, what they do usually, they deal with these components actually. Okay, calculate this component, that component, this component, that component, okay, and they don't deal with this. And it's fine computationally, okay, it's fine, I mean, there's nothing wrong with it. But, you know, mathematically, you have to keep in think that there are things attached to this, you know, each component actually, okay, and there are many